Hi, welcome to me313, Mechanical Engineering Thermodynamics. The topic of this video is gas refrigeration, and the section in the textbook is 11.9. Here are 3 learning outcomes. At the end of this video, you'll know the major components of both a basic and a regenerative gas refrigeration cycle. You'll be able to relate the areas on a TS diagram to the coefficient of performance and understand why gas refrigeration is less efficient than vapor compression refrigeration. And finally, you'll be able to solve for the coefficient of performance of a regenerative gas refrigeration cycle using EES. So let me discuss what is gas refrigeration. And so here's a diagram from the textbook. And in fact, if you just quickly look at this, this actually looks a lot like a Brayton cycle, except it's just going in reverse, where what we have is a compressor on the right-hand side and a turbine on the left-hand side, and then we have a couple heat exchangers. And that's exactly what gas refrigeration is that we're just running a Brayton cycle in reverse. And so it's just the desired products that are different, which is now going to be the QL term, which is down here on the bottom. And the work input is going to be the net work input going into this compressor that is not carried by the expansion in the turbine. And the function of the turbine here is just not really necessarily to generate some power, which it does do in helping out the compressor. But the main thing it does is it lowers the temperature from 3 to 4, because the outlet is here is going to be lower. So then we end up having a TL that is going to be the refrigeration temperature. So let's go ahead and look at this on a TS diagram. And in fact, it's fairly simple. You probably remember what the Brayton cycle looks like. And so I'm going to go ahead and go through the compressor, which is point 1 up to point 2. And then we've got a heat exchanger over to point 3, and then run through the turbine, which is point 4. And I've drawn them vertically on the TS diagram, points 1 to 2, 3 to 4, which says that they're isentropic. If they were not isentropic, they would be tilted to the right. And then 4 to 1, which is the heat input there. So here's 0.4 to 1. In terms of cooling capacity, remember, cooling capacity we know is the area under there. So there is QL. That's the area underneath that curve. And if we want to know the net work, well, QH is also going to be the area under there, and that's going to be the entire area underneath this thing. So what we realize is the net work is going to be the area represented underneath that curve right there. So there's kind of basic parts of gas refrigeration. Let's talk about regenerative gas refrigeration next, which is what we've done is added this regenerator, which I show right over here. And we saw this also in the Brayton cycle. And the reason of adding the regenerator in the Brayton cycle was we were able to increase efficiency. So there's just this one extra component, which is a countercurrent heat exchanger. So let's look at this on the TS diagram. And again, it's going to look a lot like the Brayton cycle, regenerative cycle. We're just going in reverse. But let's go ahead and review that. And so point 1 to point 2 is going through the compressor. So this is point 1. We go through the compressor up to point 2 at a high pressure. And then we have this heat exchanger, and this is QH, going over to point 3 right there. So this is QH. And then now we go through this regenerator, this countercurrent heat exchanger, going from point 3 to point 4, which is right there. So what we've got is the regenerator, heat going from one stream to the other. I'll go ahead and call that Q regen. And energy is staying within the cycle, but just moving between the streams. Then 4 to 5, we go through the turbine. And then this is the outlet of my turbine. And then this is going to be QL. This is the low temperature. This is my desired product. And this is where energy is absorbed into the cycle. It's removed from the refrigerated space, the QL, and then that goes up to point 6, and then point 6 goes through the regenerator up to point 1. Now what's interesting though is, remember the regenerative Brayton cycle had a higher efficiency by using a regenerator. So therefore you might think that this regenerative gas refrigeration cycle would have a higher coefficient of performance. But it actually turns out that's not true. So remember, the coefficient of performance for regenerative cycle is QL over the network that goes in. And so, and again, on these diagrams, remember that QL is going to be the area underneath the curve right there. If we're using a regenerator, we've only got this little area right down here. That is QL. If we didn't have the regenerator, we'd have this entire area on the right-hand side. Now, let's look at the net work. Well, the net work is pressurizing this gas from 1 to 2. And so that's not actually going to change. And then expanding through my turbine between those pressure limits, that wouldn't change either, because I'm, again, moving through the same pressure limits. So I would expect the net work to be same, but using a regenerator, QL is lower. So therefore, the coefficient of performance for regenerative goes down, in which case you might say, why in the world would we ever use this? The reason you use regenerative gas refrigeration is they tend to be colder. And so let's review why that is colder. The reason it's colder is a consequence of, look, as we go from points 2 to 3, where QH is happening. This energy is getting lost, and normally this happens to the temperature of the room that our refrigerator is in. And so point 3, which is the point right up there, can never be any colder than the temperature of the room. Otherwise, we wouldn't be able to lose any heat. And so if this is point 3, if we didn't have the regenerator, we would then end up, let me change that pen color, so I draw on this a couple times. If I didn't have the regenerator, my turbine would be right there, and that would be the coldest temperature in my cycle. This point right there, instead of this point 5. But by using the regenerator, I'm actually able to get much, much colder temperatures. So the point of the regenerator is not to increase the coefficient of performance, it's to actually increase my lowest temperature in the cycle. So this right over here is, this right over here would be TL without the regenerator. And let me erase that, it's on in green. This one right over here is going to be the lowest temperature with the regenerator. So I end up with a much lower temperature, although I have a lower coefficient of performance. So that's kind of the point of using this. And in fact, we can tell if we were to go ahead and make this regenerator smaller and smaller, so just imagine I made it shorter and shorter, I'd be slowly moving 4 up, I'd be moving 5 up each time. This is just going to slowly progress its way up that, and I'm going to have a higher and higher low temperature. So the point of regenerative gas refrigeration is to have a low TL, not necessarily to increase my coefficient of performance. Coefficient of performance actually is going to decrease, and we'll see that in the example we're going to do on the ES here in just a second. Okay, so here's the problem that we're going to do in the ES, and this is going to be a regenerative refrigeration cycle. So let's look up at what we're specifying. We're going to use air. So there's my properties of air. I've got my value of K, the ratio of the heat capacity, and then my value of CP. And so just for simplicity, we'll go ahead and assume a constant heat capacity and the value of 1.005, which will also give us a constant value of K. Now we can focus more on the refrigeration cycle. And so we're going to have an inlet into my compressor, and we'll say that that's 0 degrees Celsius, and the lower pressure will be 100 kilopascal. We'll work at a pressure ratio of 4, and so we'll have the temperature of the room, and that is 0.3 as 30 degrees. So that says that that's the coldest that we can get by losing temperature to the room. So going from 2 to 3, 2 is the outlet of the compressor, to 0.3. Now we want to go ahead and say we want our refrigerated space very cold, maybe minus 50. And so that's going to be 0.5. And so those are all specified. And I've put these all in Kelvin because the relations I'm going to use are required to be in Kelvin. So those top points are just specifications of the problem. So let's go ahead and look at our compressor equations. We have the pressure 2 is just going to be the pressure ratio times P1. And now I have my isentropic relations using a constant heat capacity. P2 over T1 is P2 over P1, the K minus 1 over K. And then in my heat exchanger, it just says that the pressure doesn't change, so 3 is 2. And then we're going to go through to the turbine, so I'm going to have to say that 4 is going to also be equal to 3. And then I'm going to go ahead and go to 0.5. So going 2 to 3 to 4 is all the heat exchanger. The top one is in the room, and the second one is in the regenerator. And then again, I have an isentropic turbine. 4 over 5 is T4 over 5 is P4 over P5, so K minus 1 over K. And then I'm just saying my regenerator is just an energy balance, and the temperature differences are the same. So fundamentally, that would actually be the changes in enthalpy, which is Cp times the delta T, and I've just dropped out the Cp. And finally, I'm going to go ahead and solve for the coefficient of performance. So QL is the points between 6 and 5. And then my work input, I have my compressor work, which is 2 to 1. But I need to subtract out the help I'm getting from running through the turbine. I'm going to have those direct coupled. So I'm going to subtract out T4 minus T5. And again, I've canceled out the Cp term. So the work is Cp delta T, which is the change in enthalpy. And then finally, my coefficient of performance is QL over the work. So we should be able to go ahead and solve this now. And so let's go ahead and let's look at our array table first. So here's our array table. We've got our pressures between 100 and 400 kPa. And we realize our lowest temperature is 203. And this is in Kelvin, so that's a minus 70. And that's my low temperature in the entire cycle. If we look at my coefficient of performance is my 1.437. And actually, I just realized I misspoke in my comments over here. I said that this was minus 50 degrees Celsius. It's actually minus 70. So let's go ahead and change that. So sorry about that. I just misspoke in terms of what my comments were. All right, so my coefficient of performance is 1.437. So let's find out what happens if we go ahead and increase T5. That's what we were saying. We're going to move T5 up, our lowest temperature, and we'll see how that actually does decrease my coefficient or increase my coefficient of performance. So I'm going to do that with an array table. So I'll go ahead and I'm going to comment out T5 and create a table. This will be a parametric table. And let's go ahead and look at what the effects are of T5 on the coefficient of performance. So I'm going to go ahead and have that start at its value, which I had at 203, which was minus 70. And let's go ahead and just increment that. Oh, we'll increment it 3 degrees. So we'll end up incrementing it 30 degrees. And let's go ahead and look at this. And so then if we solve that table, we see indeed our coefficient of performance is going to increase as the temperature, the lowest temperature in the cycle, increases from 203 to 227. Now, one of the things you want to be careful about is you want to make sure that T5 doesn't ever get any warmer than essentially, I'm sorry, that T4 doesn't get any warmer than T3, which is the temperature of the room. And so we can actually go ahead and add that. So I'm going to go ahead and add a column. And what I want to do is add T4 to this and solve for that one as well. And so the thing we want to be careful at is, remember, this, as we see, as T5 increases, T4 is also going to increase, and T4 is the outlet of the regenerator. And we don't want that any warmer than T3. So if you remember, we specified T3 at 323. And so what we see is that as soon as T5 is 218, we're actually ending up with a regenerator that is not actually doing any work. It would actually have a negative effectiveness. So there's a lot of little kind of sanity checks you want to do when varying different properties within these refrigeration cycles.